Okay, let's get started. So this is just a continuation of the previous stream where we were talking about this really interesting project called CubeCL. And so uh, what we've got here, so we discussed, how you could take something like your, basically you could write GPU kernels uh, using just Rust, and then have them, uh, you know, effectively have them run on the GPU. It's not that, Rust exactly gets to run on the GPU. Your Rust kernel gets translated into one of these shading languages that we discussed, which is one of these. Um, in my case, or the one that I was demonstrating was uh, WebGPU's shading language, which is WGSL. It's also called WGSL, this one. So right now, the CubeCL project focuses on uh, two different pieces or two different runtimes or backends. One is the WebGPU backend, and the other one is the CUDA backend. So the WebGPU backend is what I'm sort of discussing, or not discussing. I'm just going through that. But I believe much of what we discover here will be applicable to the CUDA backend as well. So in the previous stream, we talked about, the two different ways of programming GPUs. You've got the shading language approach, and then you've got the single source approach. So, and we talked about, the uh, shading languages having a history. I mean, their history, they come from the graphics world, whereas the single source approach usually comes from the compute world, specifically something that was pioneered by NVIDIA with their CUDA thing. So we sort of looked at all those pieces. Uh, and then we then moved on to the high-level CubeCL architecture. We talked about three very specific things: the compute client, the channel, and the compute server. The compute client uses the channel to communicate with the server. It's basically just data structures. Uh, the compute client wraps a channel and a compute server, and then you would be able to have multiple compute clients sort of communicate with the compute server using a channel. So we went through all of that, and I specifically talked about one particular backend, in this case, the WGPU backend. And we talked about a whole bunch of things in there. And then we briefly took a look at, what does writing kernels in Rust look like in kubecl? You simply have to annotate a function with this particular, you know, uh, cube macro or cube launch unchecked macro, and then you magically turn these things into Rust, or sorry, kubecl kernel functions. But effectively, what's happening is this stuff is being translated into, you know, into one of those into one of those shading languages or CUDA itself, and that's what gets compiled down into your actual GPU kernel code that runs on the GPU. That is. So we sort of went through all this, and we looked at much of the infrastructure, and we primarily looked at, okay, you start from here, and then what happens? How do you actually launch this kernel? So we went into those pieces. We talked about the kernel or this macro expanding into an actual Rust function. And we looked at that over here. For example, uh, if I'm not going to expand it because it's already expanded. So stuff, this stuff expanded into this, this entire macro. Let me make this a bit bigger. So it expanded it to the entire macro. You can see that, after the expansion, this is what it looks like. It creates a module called GLU array, the names of the function itself, and then it's got this particular thing. This is your actual kernel. Uh, this data structure actually represents your kernel, and it implements something called the kernel trait, making it a kernel. That's sort of the abstraction that has been put together by the kubecl project. So we looked at that, and we also looked at the fact that, anything, you can't just go ahead and write a random Rust function and then call it a kubectl kernel. kubectl kernels are basically uh, functions that only take kubectl types and then probably only return kubectl types as well. That's something that you need to keep in mind. But effectively, that's what we saw. So we ended up with looking at the kernel, the implementation of the kernel trait, and then we saw a bunch of pieces like the kernel launcher and how do you end up, how do you go from this part, which is you've already seen this in the example. So let me just do that again so that we're not missing out stuff. So this is what you write. So you have your main function, which calls the launch function. And in the launch function, you end up calling launch unchecked. This launch unchecked is not per se written by you. It's actually the expansion of the macro. So you end up calling it. And how do we go from here all the way to actually going ahead and doing the translation and then running the kernel? So we didn't look at the translation part, and then we didn't look at the launch part. So the actual launch part, we just looked at, how do you go from launch unchecked, and then there's a bunch of intermediate steps that actually happen. So we looked at all those pieces. Now what we look at is effectively how you do the translation. What is like, how does CubeCL actually perform a translation? We look at that part. So without sort of jumping into too many pieces, let me just go to the launch part. We've seen all of this. You can look at the previous stream for this stuff. So if you see there's a particular server implementation that implements the whatever server trait that you need to implement, but it's in our case, it's basically the WGPU server. So we in the previous stream we talked about this where we saw that the client actually goes ahead and sends basically invokes the launch method, the kernel launch method on the GPU server, because it contains the GPU server is the one that actually holds all the web GPU resources, like your device, like your queue, and the other stuff. That's part of the web GPU crate. So you've got all that, and then we saw that effectively what happens is when we call the execute method on that, the first thing that you do is you go and set up a pipeline. And as you can see, setting up a pipeline for it simply means that you are going to go ahead and call kernel.compile. And from our previous stream, you would know that this kernel is effectively a GLU array struct. And when we actually call compile on it, we'd be taken to a bunch of places. I'm not going to, like, you can dig into the code and follow along. But effectively what ends up happening is you get to this implementation of kernel compilation. So there are two steps, as I've noted here. The first one is kernel expansion, and then the second one is kernel definition. So let's look at the expansion and the definition. So what actually happens when you want to call define? You've already seen this method before. Where did we see that? We saw that here. You saw that if you implement the kernel trait, then you're effectively a kernel. And then it's got two different methods. One is the define method, and the other one is an ID. The define method returns the kernel definition. And that's kind of what we wanted to do right now. The kernel definition is nothing but it is essentially CubeCL's intermediate representation. And we kind of saw that in passing the last stream towards the end. Now we'll sort of dive a little deeper into this. So what actually happens over here? When I basically call define, well, it's going to take me back to the terminal trait, but in our case, if you want to go look at what define does, you already saw the expansion. When the macro expands, it actually generates a Rust function. That's what macros do in Rust. And then you will see that here's the definition for define. So there's a bunch of things that are happening over here. We'll go through them. The first few items are all, there's some ceremony that's happening. Because what does the kernel, if you want to translate something, what do? You actually look at the parts that make up the kernel. That means the kernel takes in some input, and there's probably some output. Um, and then you also want to ensure what are the contents of the kernel. By that, I basically mean if you were to, let's expand this a bit. What happened? Yeah. So by that, what I mean is, if you look at this entire thing is the kernel, right? The one that's written in Rust. And then these are your inputs. This is your input, and this is also your output. So kernels technically don't return anything, don't return any output. This all you supply, your outputs as well as arguments, and then you sort of write to them. That's how you read them back. And then this is the body, right? So how do you take this body and sort of map it to uh, you know to the end result that you want? In this case, you want your web GPU shading language, which sort of looks like this. Where is that? Yeah, this is your web GPU shading language. Let me just sort of move this out. If you see this, this is your web. So it starts from here. All right. This is your this is a typical web GPU kernel or web GPU shading language kernel. All right. You've got, some variables. They're marked this way. Forget about, these things. I think we sort of talked about it in the last. These are all bind groups and bindings. We'll get to that part. And then you've got some constants. You've got your main. You've got your work group size. And I'm assuming that you already know a little bit about, working with GPUs. But I'll explain this. So the work group size is, because GPUs, the difference between a CPU and a GPU is that you can pretty much, um, you know, you can launch a number of threads in parallel because it's a pretty big parallel machine. That's what a GPU is. Rather than focus on latency, you focus on throughput. You might technically have high latency because of all the communication that goes around, but the fact that you can launch a lot of things at the same time and get them going is what makes the GPU really effective in parallel workloads. And without going into a lot of detail in that place, which maybe we'll do sometime later, a work group size, in the CUDA terminology, I guess this is basically block size. You see, you can launch these threads. So you can actually have threads in X and Y. I don't even know why they do it that way, but fine. Um, Effectively, you just multiply all three things, and then you say that, okay, these the total number of threads I want to launch. So 4 times 1 times 1. So you actually want to launch 4 threads. Why? Because we're actually working on 4 different elements at the same time. So 4 different threads for 4 different pieces of data. That should, you can say, that should be enough for this particular example. And then again, same stuff. It's like the concepts that you see in this web GPU shading language are pretty simple. Of course, there's a lot more, as you dive into the spec for web GPU shading language. But right now, let's just look at what's over here. So you've got the let binding, so web GPU is inspired by Rust. So some of the concepts are actually taken from there. And then you've got, again, another, think they call directives, but anyway, built-in variable, this one. So you've got that, then you've got a bunch of variables, and then you've got an if statement, and then you've got your regular functions. And this, if you look at this function definition, it looks very much like Rust. That's what I meant by WGSL looking a lot like Rust. Yeah, that's about it. This stuff looks very simple. So you want to take this code, where the hell is that? Yeah, you want to take this stuff and convert it into basically the stuff. You want to convert it into the stuff, right? So how do you do that? Well, this is not like a character to character transformation, etc. You want to understand the structure of your Rust kernel, and you want to understand the structure of your target kernel, which in this case is your WGSL kernel, and then you want to have a very methodical way of going from one to the other. So that leads us to the first part, which is expansion. What does that actually mean? As you saw, the first thing that you do is when you hit the define method, there's a bunch of things that happen. You actually create two B-tree maps for all the inputs and all the outputs that you have you've provided the kernel with. And then you register the input and you register the output. All right. The registration is basically using the kernel builder struct. So the kernel builder is what's building this CubeCL IR for you. Okay. CubeCL has its intermediate representation. We have seen that in the last stream. I will go over that again, which is what I'll be doing most of my time in this stream. But basically, you're going to have the kernel builder. It's got a context. It's going to have inputs, outputs, indices, and let's just look at it. It's going to have this structure. We're basically going to be populating the structure with the relevant pieces. So the first thing that you're going to need to do is you're actually going to need what inputs am I providing? What outputs am I providing? And then you want to convert that. That's what I mean by expand over here. So when you say expand, you basically want to translate you want to take this information and put it in your IR, in the CubeCL IR. All right. That's kind of what's happening here. Here, the same thing also, again, this is the same thing as well. So you expand the output. If you just expand it, presumably you're just expanding the input. It would be nice if you just call it input, but fine. And then what happens later is, yeah. So once you've actually, let me get to this part first. I made some notes because there's a lot of indirection going on because, as you can see, we're dealing with the macro stuff. So yeah, kernel definition begins with instantiating the kernel builder struct, and then you populate it with the kernel inputs and outputs. This is generally done, this is generally done with the ordered maps, which is the B-tree maps. You use that to go ahead and convert them into what is called variables. Now, these variables, this word variable that you see is very similar to what I just showed you. Where did I show you? So you just saw WGSL, all right? You saw variables over here. This is WGSL's variable. But if you want to see CubeCL variables, we want to actually construct them. So we're going to actually parse whatever's in the Rust kernel as inputs, and we say that, okay, this is one variable. Just hold it as a one, store it as a variable, CubeCL IR variable. All right. So that's what we're going to be doing throughout. The expansion is basically going to be trying to convert whatever Rust code we have into this intermediate representation. That's what an expansion does. All right. And you can see that this is inserting it into the B-tree map. This is inserting the same thing into the B-tree map. Whatever expansion we've done on the output, whatever expansion we've done on the input. Right? I'm not going through all of this because, we'll just get the basics first, and then we'll get to the rest of it. Okay. Now that that's done, and yeah, one more thing. When you actually look at, when you actually do what is called this conversion to variables, or it's actually called registering the inputs and the outputs, what you get back is an element. This element is actually an expanded element. And the word element over here basically means some construct in the CubeCL IR. That's what it means. It's some construct in the CubeCL IR. So if I look at it that way, that's why I've sort of defined a couple of things as the way I look at it. So expand element and expand element type are both just variables. They're wrapper types for variables. And then once you have a fully initialized kernel builder, that means you've got the expanded kernel inputs and outputs. Then we can get to the body. the kernel's body for expansion. In here, we need to be looking at just this part, right? This is the body of the kernel. We only need to look at this part. But before we go ahead, let's look at a couple of things. If you were to think about pretty much, if you were to look at any GPU kernel, there's ultimately speaking, there's just two constructs that you could sort of distill the entire kernel into. One is the operation, the other one is the variable. So operations require operands, and those operands can be variables. That's it. So CubeCL operations basically are all of the operations that are legally possible, or you can use all of the operations that can be legally used in a typical CubeCL kernel is what we're referring to by operation. Or rather, all the operations that can actually be used in the end GPU compute shader, that's what is a legal operation. And then variables, I think we already discussed them. These are basically things that are holding some value, and they can be used in GPU compute shader operations. Now, scope is a construct, or rather, it's an abstraction that's used in CubeCL, which it's pretty straightforward. It's a container that holds operations and variables. So if you think about it, the effective thing that you're doing is you're going to build up this entire IR. So you want to collect all the pieces that make up the kernel that's written in Rust in your intermediate representation. That's kind of what scope keeps track of. And then cube context is, again, a wrapper type for scope. But effectively, you can hold multiple different types of context. That means you can have a global context, you can have a local context sort of thing. So all of those things can be held inside a cube context. And then we've already seen expand element and expand element type are basically wrapper types of variables. The typed one is the typed version. That means you also keep the type information along with you in your IR. So that's pretty much some of the important types and structures, data structures that are used in the kernel expansion. Now, let's go step by step. Let's take a look at this. If is the first statement. And then you've got absolute POS is less than input length. So if you look closely, this is actually a function, right? And then this is probably a constant. And this is, if is basically a control flow keyword, right? That's how we look at it. So if you just forget the if part, look at the first part, which is this. What happens here is we effectively get into the expansion mode over here. So let's actually expand that. The way that actually happens is through this function called expand. So when the macro expands, this is what it produces. It actually produces an expansion for all of this. So if you see here, the first thing is the condition. And that condition, the left-hand side of that is going to be expanded itself. And then you expand the right-hand side of that. And then you also expand the operator or the operation between these two operands, right? So that's kind of what this first statement does. And then that is stored as your condition. And then after you have a condition, then you do the full if expansion. Now, the if statement has three things, right? It's got an if, it's got a condition, it's got the bug. That's kind of what we do again over here. So before we go to the if expansion, let's just actually look at the first part. Let's look at what's happening when we do absolute expansion. So here, one of the things that you should also keep in mind is when you start looking at this, what is absolute position actually? When you look at that, you see that uh, absolute position it's actually not used either in CUDA or WebGPU, but in a collection of threads that you're going to launch. All of these threads are actually indexed and numbered, and I'm not getting into that part for GPU programming. I'll get to that. But know that all of these GPU threads are actually indexed, and you can pretty much retrieve them, basis the indexing mechanism that we use. CubeCL actually offers stuff that these two do not offer. That means if you have a grid of threads, a two-dimensional grid of threads, you want to know which thread. You could use the absolute position of that. Uh, In the other two, that is in CUDA and WebGPU, you sort of calculate it. For example, if you saw the XLWGSL code, you see this long thing that actually happens here? It's effectively calculating the absolute position in your grid of threads, your launch, whatever you've launched, the work that you've launched. You want to figure out, exactly where your thread is in that, launch. This is how you calculate that. But here, what's happening is CubeCL provides a simple abstraction saying, we'll just go ahead and write it. We'll just go ahead and offer an option, not go through that because our translation becomes a lot simpler. We don't have to worry about this entire thing, right? So that's easy. So absolute position is a variable. Then that's why it gets expanded that way. And then input.length is the RHS. It's also a variable, right? But the important thing is before you actually do input.length, you need to calculate length itself, or you need to expand length itself. So let's sort of do that. If you see that here, you should be able to see, yeah, you should be able to see that. First, you expand the length. And then after expanding the length, then, whatever comes out of that is what, you store as your RHS. I'll anyway sort of, this might sound a little abstract because you're basically doing source to source translation over here. So just keep that in mind. Unless you've done this before, it takes a while to wrap your head around this. But let's look at the simplest case. What happens in the simplest case? So if you go here, yeah, so for constants, there's another macro again that you want to expand. So we can go look at the macro. So when I do absolute position and expand, I sort of come here and I'm saying, okay, go ahead and expand this particular macro. So you're passing an absolute POS, then you're saying, this is the variable that I want you to link it to, and then there's some documentation for it. If you went ahead and looked at constant, you would see that, it, in other words, expands to this element, and that element is basically a typed version. That's it. There's nothing else. There's no fancy thing. You're just converting this to a CubeCL IR variable. That's what expand element typed is. The interesting thing happens when you start looking at the next section is when you start looking at expand length method. By the way, all of this, you sort of need to do all of this for every other expanded element typed thing, right? So you'll be able to see that over here. So the first thing that you probably need to do is expanded version of length. So if you just follow this method, you'd be able to see that the context over here is the cube context. This thing comes specifically from your um, kernel builder. All right, you have that. So the first thing that we need to do, as you can see here, when a new variable is required, we checked to see if we can reuse an old one or otherwise create a new one. So yeah, I mean, rather than me just talk about it, let me go ahead and show you what actually happens. So you're going to go ahead and create a local variable over here. So you either check if it's an old variable. If not, you basically go ahead and create a local and then put it in there, right? And then there's another option to say if it's atomic, you do something else, etc. But this is the two important things. And every expansion has these two steps. Usually, the local stuff may or may not be created depending on what you're expanding. But ultimately, what happens is into the cube context. That means if we go back to our initial explanation, the scope is a container that holds operations and variables. You want to go ahead, and the cube context is basically a wrapper around the scopes. So you want to go ahead and register each operation and variable that you find in your uh, in your Rust kernel. You want to sort of find them and then store that information in your CubeCL IR representation. That's what we're going to be doing, and that's what this register function does. So you got to go ahead and register stuff into your scope. If it's an operation, you register the operation. You also register your variables that the operation uses. So you do all of that for each expansion. Pretty much that's what happens. All right. So, and then you also see there's some amount of cloning that's going on. Uh, I didn't look into it because I presume, um, yeah, I don't think this stuff, the array stuff, is clonable. Oh, sorry, it's by default copy. So that's kind of why you're doing this. I'll need to look into that a little more. But anyway, you go ahead, expand the length element, and then you have that as your right-hand side. Again, all of that all we're doing is we're just looking at this particular portion. Better ways. We're just looking at this particular portion. That's it. And we're expanding that. And then finally, the last thing that we do is we expand the less than operator, which is this. Expanding the less than operator, again, you can see, if you go ahead and look at it carefully, you have got another indirection over here. Forget about, the whole vectorization part and the local creation part, etc. You will see that this operator, which is we are passing in an enum over here. So we're just saying that in the CubeCL IR, if you come across the less than, that has to be nothing but a lower. Where is that? Yeah, that's this. And then I want you to go ahead and, expand it accordingly. Take the LHS and the RHS and the operator, and then, sort of store that as one operation. All right. So if you take a look at that again, you got the LHS and the RHS. Vectorization, we're not looking at that at this point. You get that operator, it says it takes this, it takes the left-hand side, it takes the right-hand side, the output is what we get over here. We want to register that in our context again. So this pattern is what keeps repeating itself over and over and over again and again and again. That's kind of what expansion does throughout. So now you want to expand the if statement, same thing. You pass in the context, then you talk about the condition because an if statement has a condition and has a block of code. So that's sort of how you pass. So this is this is our closure or lambda or whatever you want to call it, and you are passing that to the if expand. So if expand does the same thing again. We're simply going ahead and building this whole thing up. At the end of it, you'll be able to get an operation, and then you register that operation with this condition and the scope over here. Some things that you do tend to get into is, which is what I talked about. You also want to understand scope in the sense when you write something like this, for example, if you want to generate voxel code that looks like this, you know that this scope is different from this scope, right? You want to actually differentiate that. So those are two different scopes. It's kind of what you'd also be capturing as information. Okay. So yeah, that's why you also have a child scope in the if expansion piece, which is the block. And then again, I don't think I have to repeat all of this because it's the same thing. So if you were to look at our code over here, now this statement is done. Next, you come to the statement. In this statement, what do we have? We've got something that's indexing into an array, which is output is the array, and you're indexing into that array with absolute position. And then this is a function that's also taking an array, an element that is, and that's that we got by indexing into an array. So firstly, we need to figure that out. How do you describe that situation? And then you simply go ahead and also expand the GLSL function out. So the way that works is, again, output is this output. And then this is one thing that was very interesting because we seem to be doing the same expansion twice. I'm wondering if you can, if there's a way to simply like reuse that, right? Why do you have to do it twice? Yeah, it just gets difficult if you want to like keep that information throughout once. But for now, I think it's fine, is my guess. It gets difficult if you try to reuse this from in this context. Okay. All right. So let's go ahead and look at the remaining pieces. So you got that. You've got the index. You got the array. You got the index. Now let's look at the second part. The second part, we're actually talking about this function. It returns a value, right? Some value. We don't know what value, but some value. That's why it's called value. And then we say, uh, again, there's an array and there's an index. We do both expansions. And lastly, what we need to go ahead and do is we need to sort of index into that. So you do array and this, and then you need to index into that. And that's sort of what you're doing over here, right? Here, you're not just going to be doing an index, you're going to be doing an index assignment, which is what this is, right? And then you can expand that. So I'll just sort of explain the expansion on this part so that you can sort of look at the remaining pieces. Uh, so if you go ahead and look at the expansion over here, it's not very different. You go ahead and get the index, and then you look at the array, and then you do a binary expansion. In this case, it's not a vector, so it's an array. So you pretty much want to go ahead and do that. So if I sort of went in here, at some point you will see that we register the same operation along with the operands, right? So there's a lot of work that's happening to ensure that we get the operations and the variables accordingly the way that we want them to do so. Yeah, so that's pretty much how you would do an expansion of an indexing operation where you have an array and you want to index into that. This is sort of what you do. And similarly, again, you can go check the expansion for the index assignment. So once you're done with all of this, right? And it's what I mentioned over here. Absolute position is a variable, input length is a variable, the less than operator expands to with the context. All these operations are added to the provided context, which is the scope. And the order in which they are pushed is very important. So I didn't talk about the scope. So let me actually go and talk about the scope a bit, because the scope is sort of important. When I keep saying push the operation, register the operation, etc., what do I actually mean? See, it's a vec of operations, it's a vec of locals, it's a vec of shared memories, arrays, all of this stuff, right? It's basically collecting, you're basically pooling together all that information and um, into your scope. You want to keep that information around so that when it comes to the time where you actually want to translate, you can do a one-to-one mapping. I'll show you that, which is probably the last part that I can talk about. So that's the scope. Now, kernel definition. So I mentioned there's two parts. One is, as you see, the expansion. We just saw, what's expanding into what. Now, finally, that entire data structure that we created, the scope that we've created, we effectively want to convert that into, some actual IR, right? So that's what we're going to be doing over here. Once the kernel function is expanded, the next step is creating a kernel definition. So you're going to take all these pieces that you've pulled out of the Rust kernel, that the Rust function that you wrote, and you want to integrate these pieces. That's why you're going to need a kernel integrator. And then here we basically call this a kernel expansion, which means final step where you integrate these components and then you expand, and then you should be able to get the kernel definition. The kernel definition, as I've stated here, represents the finalized kernel after expansion and integration. This is pretty much CubeCL's intermediate representation. And we'll sort of look at how this works. So the first step is to instantiate a kernel integrator, and then we already saw the kernel settings part. So we need to pass that in, and then you need to call the integrate method for the kernel integrator. That's, the most important step. This is not going to do much. It's going to go through all those pieces of information that you have collected from the Rust kernel, and we're now going to embark on actually creating our IR. So I'll sort of walk you through that. How does all of that work? So this expansion goes on. There's a whole bunch of pieces. There's not just this. There's not just this, but in the GLU kernel, in the example that's written, you can see that this the GLU array actually calls into the GLU scalar. So that's also expanded out. And then you have one really nice little scope with all the operations and variables that need to be, the information that you've pulled out. Okay. The kernel definition is basically we go back to so we've done the expansion. We're done with that. Now the builder's job is, okay, the expansion is done. I've got the context. That means I've got the scope and I've got all the pieces that I need. Let me go ahead and just do build. So when I call build, the first thing that happens is I need to create a kernel integrator here. And the kernel integrator effectively goes from, we saw this, for example, you saw that there's all these groups and binding information that's present. That is what the kernel integrator also adds to the inputs. That's primarily what we do. And then we go ahead and convert the context into scope. So when so basically we created a kernel integrator, and the context is in a certain format. We want to convert that. So we do a drop of the root scope, and then we take the inner thing, and then we assign it. It's not important because you might get confused a bit, but just know that that happens. And then you get to the integrate part. This is where the actual, compilation happens, or I would rather call it translation happens. So what are we going to do? We got to look at the scope, and we got to go through all of the scope as a container, and we go through all the pieces in that container, and then we try to put our CubeCL IR together. So the first thing that happens is there's vectorization stuff that needs to be looked at. And then we register inputs and outputs. If you look at just one of them, registering inputs, you'll see that, okay, you are saying that the input, the scope, that in the scope, I've stored an input. So that's sort of what I'm going to be looking at. I'm going to drain all the inputs and say, okay, how many inputs are there? Is it an array? Is it a scalar? All this stuff. The output is a little more nuanced. You have a few more things. The output info can be an array that you're writing to, an input array, right? A lot of stuff. Not important, but that's what you mean by registering. That means this step is actually translating the information that you've pulled out and converting or constructing your CubeCL IR as far as your inputs and outputs are concerned. That's what this does. And then the next thing that you do is you go ahead and put your inputs and outputs. And I sort of mentioned this somewhere. The first step is to instantiate the kernel integrator, which is what we're doing, and then call the integrate method. This method combines the inputs and outputs into input-output bindings. That's the first step. And then obviously it returns kernel definition. But before returning the kernel definition, we need to get into the body of things and then do a little more. So let's get to that. So the first thing that happens over here is, one is we've already looked at the inputs and the outputs. And then you create a vector with capacity 2, and then you say I got a named. Uh, Wait, why are we talking about the named thing? Oh yeah, yeah. So um, in our uh, kernel, we have this info. We have a named portion. Let me see if I can find that. Yeah, see, there's an input, there's the output, and there's also this info thing, right? Uh, we also have this, which is nothing but an array of U32s. But we also have this. So that's sort of what we're referring to in, where is that? In the integrator here, where we go ahead and create a named one as well. Because if you look at our uh, what is that? Yeah, if you look at our kernel integrator, wait, correct. You would have named bindings, you have the input-output bindings, and then you actually have the kernel expansion. Those are the four fields that you need to look at. That's sort of what we're going to be doing here. All right. And now, once that is done, we are going to go ahead and push that named thing that we just got out of here into our bindings. That's fine. And this thing returns the kernel definition as inputs, outputs, named, and then self.expansion.scope is something that you've probably seen here. Uh, I, some of this stuff. Yeah, right. Sorry. So you return the kernel definition with the scope, the input-output bindings. You've got them back, and sorry, you've got them back, and your builder. The kernel builder has now built the kernel definition. You have it with you. The next step that you see over here is, so we're in the define method. And if you remember from our earlier case where we saw somewhere, this is the amount of, work that yeah. So the definition over here is what we wanted to do. So we got the kernel definition, which is great. Now we've sort of pulled the parts out. We've put them in a structured fashion. We're calling it our kernel definition. We will spit it out and we'll be able to see that. And then this part that you see, which is the kernel compile section, you want to actually go ahead and compile your whatever kernel definition you have right now. You want to translate that into your actual WGSL code, right? That's effectively why we're doing all of this. So that's where it happens over here. Here, C is what? C is something that implements the compiler trait. So for the WebGPU stuff backend, we already have a WebGPU compiler. So in order to take a look at that, I simply go into CubeCL-WebGPU or WGPU, and then look at the core compiler section, and then I'll be able to find the compiler. This is the compiler that is going to be used to do the compilation over here. Okay, it's going to call compile. So let's actually go ahead and look at it because it's going to be passed in the kernel definition and the mode. The mode is not important, but it's going to be passed in right now. If I see that, compile shaders, yeah, that's fine. File element, variable. Okay, where is compiler? Only compile, only compile. Yeah. So as you can see here, the WGSL compiler implements the compiler trait. So it goes ahead and gives us the compile method, and you basically instantiate it and call compile shader. Compile shader does the rest of the thing. And here's where you will like to see what's actually happening. So the first thing that actually happens is, you look at the number of inputs and the number of outputs to the kernel definition. That's what we pull them out. And then the main point, the main thing that happens is we look at self, which is WGSL compiler, and say compile scope, right? If I were to look at it, I simply see that, we're going to go ahead and look at the scope, and then we're going to call process on it. And what does process do? This has changed a little bit because this was actually in the separate place. We are pretty much going to go through each operation and each, all the variables associated with an operation, and then we're going to cycle through them and figure out, all the operations that exist. That's kind of what's happening here. And that will allow us to look at each operation and then, sort of translate that into some WGSL code. So let me see if I can find that, sort of set some place for you. Returns the variables and operations to be declared and executed. Note, new operations, let me actually do this. New operations and variables can be created within the same scope without having conflicts. All right. So this, I presume, has changed a little bit in the last time I looked at the piece of code because I've only had very limited time. So basically, all the operations and all the variables have been pulled out, and you get the scope processing, and then optimize returns the scope, the processed scope. So that's, I believe, what happens over here. Okay, did I miss something? Yeah. So you get the scope processing out, and then now that you've got the scope and that's processed, you know all the operations and the variables that exist. Let's just loop through them. Let's go look at the variables first and say, okay, if it's a variable, if it's a slice, we don't care because obviously you can't actually, reference slices in your data code. But if it's an instruction, sorry, for each variable, we're going to go ahead and say, okay, declare the variable, compile the variable is going to be the compilation step over here. What sort of variable is it? Is it an input? Is it a global scalar? Blah, blah, blah. See, every time we look at the CubeCL IR, we map it to the actual WGSL IR. So there must be a place where the WGSL IR is actually, present. So the way to sort of look at that would be if I went ahead and looked at it, I would see that this is the complete WGSL IR or the WGSL representation that you'd want. So we're basically converting whatever CubeCL IR we have into the WGSL IR over here. Great. So this is an example of compiling variables. Now let's get to the last part so that, I can just wrap it up. Then you look at the processing and then you say, okay, compile operations. Operations right here. And you already seen that if it's a CubeCL operator, I want you to compile that into whatever. So there's variations in the operations. You can have procedures, metadata, branch, etc. All that. We'll just look at the operator part because that's the simplest one. Compile the instruction. Again, same thing. You have your CubeCL IR, which is, let's say, in our case, it was lower, right? Where did I go? Yeah, this. This will be converted into the WGSL, instruction lower. So if I was to look at that, it says the same thing. All instructions that can be used inside a WGSL compute shader. So there's a one-to-one mapping. So you basically convert it into your CubeCL IR, and then you should be able to do a one-to-one matching of that into relevant pieces. All right. Now, once you're in this format, once we're in this format, we've got our instructions. So we've compiled the scope. Then if there are any extensions, we've already registered the extensions as well. Like there's a bunch of things that you can do. And then finally, go ahead and create your compute shader, your WGSL compute shader. That means you take the inputs, the outputs, the name values, all of that. And here's what happens towards the end. You're going to do compile visibility. So in the last step, when you're actually doing this compilation, you'll be actually hitting this part where you're actually writing the Wixel code. So let me help you with that as the last piece. And then I think we've pretty much extended our time. We can collapse this. So you get to the visibility part, you get to, so this part is pretty straightforward for your inputs and your outputs and all of that. There's the last part. Mm, okay. Right. So we here, we got the low-level IR, and then the low-level IR is basically this compute shader thing that we already saw. So is this compute shader thing? Yeah, this compute shader thing. So we've already created all of this. When we're creating all of this, so what happens is when you actually have a compute shader and you want to go ahead and display the compute shader, that means whatever structure it is you filled in. If you want to go ahead and display that, it's actually going to go ahead and write pretty much everything that you need. That's it. Because it's a source to source translation, right? So you need to go ahead and actually do the display over here. And let me run the code so that you can see this happening in real time. So we've seen the CubeCL IR. Let's also see the low level IR over here. It should pretty much be very similar to the same thing, right? Because it implements the display trait, that should be fine, right? So let's just actually go ahead and run what we have here. I think I should make this bigger. All right. So let me say Argo run examples with Julu feature, blah, blah. That should be enough. What happened? New stuff? Good. Mm, just when you needed to run something. Uh, this shouldn't be happening actually. So I need to update my instance. Right. Some random linker error. But anyway, if this thing doesn't, come back quickly, you should pretty much be able to see exactly what I was able to show you. That is, you should be able to see that this is the Wixel code that's generated, this part, that is whatever you saw here. So when I print the lower level IR, you should be able to see the Wixel code. And the GPU IR that you saw previously, you should be able to see that as well, which is this. No, this. You'll be able to see both of them. So some random error and showing up. Did I change anything yet? Nothing. Okay, I think I have a better way to do this then. Hey, yeah, this is gonna take a while. But in that case, let me just run this then. Hey, what's your problem? Hmm. Yeah, it's gonna need a thing. Okay, great. Huh? What's happening? Yeah, something happened. Looks like the update screwed up the Rust installation. But effectively, I could probably do that in the next stream. So I updated it to macOS Sequoia, and this crap happens. Ugh. Anyway, so yeah, as I said, you should be able to see this. Uh, so this is your Wixel code. You should be able to see that when let me actually close a lot of this crap. This is the problem with with stuff like source to source translation. You have to go through a lot of hoops to get this right. Anyway, so we're here. You want to see this? You can simply go ahead and see this. This is your Wixel file. This, uh, sorry, this low-level IR that you're seeing is effectively your Wixel code that's going to be generated. And uh, then you also have your last one, new. Your GPU IR should be this part. So yeah, and let me just, for the benefit, you know, everyone's benefit, let me just show you what we saw last time as well. When you look at something like Wixel, you will see that this is your kernel definition. In your kernel definition, you've got inputs, you've got outputs, and you've got named stuff, right? Your inputs will sort of have a one-to-one mapping. Now, if you look closely, you'll see that, okay, input zero is this is the global variable. It's a storage buffer. That's what this is. The visibility is read. I wonder why it's read right over there. But anyway, and then the type of element that this buffer is going to hold is of float 32. This information is not available in Wixel. It's because this is only CubeCL IR specific, because it can do things like auto vectorization. And the same thing again holds for output. The same thing again holds for the named, whatever, the named input or output, or whatever that is. And then if you scroll down, you'll also see that the dimensions are sort of the work group sizes over here. It's called cube dimensions over here. And then the body is main. Essentially, what you're doing is you're expanding the scope out again. You're saying, let's start by saying that the metadata is a global input array, and it's got float 32 elements, all that stuff. If you see carefully, you'll find the same thing. All right. And you will also be able to see the next item, which is, where is that? So let's start from where are we starting from, actually? Yeah. Yeah, we should be starting from your ID, right? If you take a look at this, you should be able to see that we have absolute position over here, which corresponds to this ID. I just want to show you a one-to-one mapping over here, because so this is an operation, and we're looking at the let operation on an input array, and then there's a local, which is this is a local variable. Again, this is a U32 integer. Why is that being pulled? Let's look at this. Mm, Okay, let's look at it this way. So you've got the array length here, which is what this is referring to. It takes an input array, and then you get the L00. Yeah, and then that is effectively our U32 here. So we've already seen that the global input array is, takes F32 elements. So that's kind of what we're taking in over here. And then we're also taking in, okay, yeah. So this is the input, and this is going to be the output. So yeah, the input is this, which is your array and the entire thing that you need at the array length. And then the output is a local that we're creating. This local is a uint, which is what we see here. All right. And then that local that you've just generated is what goes in to your into this particular operation, which is you're checking whether it's lower than, right? So whether the ID is lower than L00, right? The ID is over here. That's kind of why you have absolute position. And then you take the RHS, which is the ID. There's an operator that's happening. What is the output of it? You either get a true or false, right? So it's a Boolean. So the local is a Boolean over here. And that is L01. That moves in to the if statement in the next one. Likewise, the whole body is expanded out. Okay. So you'll also see a bunch of local declarations as well, which I presume is what some of this stuff will be. Anyway, so yeah, so that's there you have it. That's the full just to recap. That's basically how we expand the kernel, and then once the expansion is done, we go ahead and sort of pull all. That means once we go ahead and pull out the pieces of information that we need, we construct our kernel definition from it. And then once we construct the kernel definition from it, we simply do a one-to-one mapping between CubeCL IR and the target IR. In this case, that was WebGPU's shading language. With that, we should be able to produce essentially the shader code that we wanted for the target. And then towards the end, you'll be able to see that, as mentioned, The kernel definition is the intermediate representation. The final step is to map the IR to the target shader code. Essentially, we map all variables and operations in CubeCL to the target shader source using the WGSL compiler implementation in our case. So that's pretty much how CubeCL works under the hood, right? So it's a source translation. And this is kind of why this project is pretty interesting. It's because we're not even going into the so what happens to WGSL? WGSL actually converts itself to something. For example, on the Mac, WGSL needs to convert to metal shading language, which is done by another crate called Naga, and then go through all of this. So we don't have to worry about the ultimate binary format that is understood by the Apple GPU in this case. You could sort of target WGSL, and then you could get your GPU code running. Of course, it's not going to be probably not going to have all the knobs that you need, but I guess that's where CubeCL is trying to bring in some more benefits by saying, I have a lot of information available to me up front. So at a very high level, I could probably do a lot more optimization at that end, at that level, which should translate into benefits when we actually produce the real binary that gets run on the GPU, right? So that's why this project is pretty interesting. It's a fast way to target as many GPUs as possible, or many GPU vendors as possible. I guess in that sense, it's sort of stands up to this tagline, right? Multi-platform, high-performance compute language extension for Rust. That's good. Yeah. So this is the exploration that I've been, going through, or I've been doing for, I say, the last 2 days. All right. So it's a pretty interesting project in my opinion, and I think there's a lot more that this can turn into. Now that I have a handle of things, I'd see how I can go ahead and contribute to the project, which I guess should be another stream. But anyway, uh, getting to write an actual kernel should be the next step. Probably we'll do that in the next stream. All right, so that's about it, I guess, for today. Thank you.